And now recording. All right, so I've already finished everything we need to cover for the test, and I'm just going to go on. So I'm up to 16.3. So my goal is 16.3, maybe sneak in some of 16.4. But to remember, we're not really as far ahead as you might think because, I had to push everything back. So I think I'm a little bit ahead, but not exaggeratedly so. Okay, so 16.3. Okay, second hour, I will let you ask questions if you have any. You don't have to ask any if you don't want to. If you don't ask any questions, I may just keep lecturing and then maybe end early. Okay, so test this coming Thursday, exam 4. Coverage is just the one chapter, chapter 15. So you know the rules by now, but I'll say it again just so that there's no excuse. If anybody says, I don't know what the rules are, I keep saying it. Okay, so you submit 15.1 to 15.9 for homework. And let's see, this is the day before the test. So right after class ends today, you may start submitting the homework. You must submit at least 70%, but that's very easy considering I do a huge percentage. Some sections I end up doing 70% or more, but I do a lot of the homework problems. So all you got to do is just copy what I did, and just do the rest of it. And problems are very similar to the ones that we had. Still about 10 questions, but and I know some of the problems can get really long. I'll take that into account when you do it. So once again, just like the previous test, all we'll do is the test, nothing else. So class starts at what, 6:10, so around 6:05-ish maybe. I'll send the exam on Canvas announcements, and you join as usual. This time your camera's on, true background, first and last name according to my roll sheet, so I don't have to guess who you are. Keep yourself muted. Any questions, put it in the chat. Good stuff like that. You're gonna have one cheat sheet, one formula sheet, front and back, 8.5 by 11. And a calculator, of course. After that, no other books, no notes, no people, no computers, no cell phones, and good stuff like that. Okay. And then we just have one more test and a final exam. All right, so any questions about what's happening? Check. And let's see, okay. So I think I'm caught up. I'm good with whoever put something in the chat. I'll take a look at that. All right, any other questions before we start? So again, 16.3, I'm gonna go on, but 16.1, 2, and 3 will not be on the test, and 16.4 also. And by the way, you should have gotten something from me. I cleaned up that one problem that I messed up from the previous section 9, and I got the wrong answer. But you're probably not gonna, I mentioned you're probably not gonna have to do the whole thing anyway, but for some of them, for closure reasons, you might wanna see the whole thing done semi-properly. So I sent a video on that. Again, I'll probably not have you do the whole thing because it takes too long. Might have you just do a subset of something like that, but at least I finally got the correct answer after doing your transformation. Okay, so any other questions? Let me check the chat. I don't think so. Okay, so we'll just go ahead and start. All right, so on to 16.3, maybe 16.4, but we'll see how it goes. Okay, so I'll go rapidly through what happened last time. 16.3, fundamental theorem of line integrals. Okay, so the integral of del f dot dr. Okay, so if there's a little f of x, y, z, a scalar function, you can find its gradient. Okay, if there is a gradient function there, okay, it's a vector function, which basically happens if you have a conservative function. Then we do f of r of b minus f of r of a. So that means if you have a conservative vector field, okay, it doesn't matter what path you pick, you have path independence. Okay, plug in the ending point, plug in the beginning point, and subtract. That's just like Calc 1 and Calc 2, right? Anti-differentiate, plug in b, plug in a. Here you anti-gradient, plug in ending point, plug in beginning point. So put this on your next cheat sheet. Of course, this will not be on this test. This is on our last test. Okay, and then concepts, we have path independence. All of these are equivalent. If you have path independence, meaning as long as you have the same starting point and same ending point, okay, if it doesn't matter what path you pick, you always get the same answer. That's called path independence. Okay, that means you have a conservative vector field. Okay. It also means if you pick any closed path, the integral will be 0 because the starting point and ending point are the same. So obviously, if you subtract the function values, you get 0. All right. And so suppose capital F is a vector field that is continuous on an open connected region D. If F dot dr is independent of path, then capital F is a conservative vector field. There exists a function little f. I'm going to call it the anti-gradient, such that del F is equal to capital F. Okay. For two-dimensional vectors, how do we know if we have a conservative vector field? On page 1090. Okay, if capital F is pi plus qj, the two-dimensional version, if the partial of p with respect to y equals the partial of q with respect to x, the two-dimensional flavor, then you have a conservative vector field. Okay, essentially what's happening is capital F is at the first derivative level. Okay, if you take the second derivative, the mixed partials would match if above capital F there was a little f, an anti-gradient. Okay, where you're going to do fx and fy. So if p is fx and q is fy, then if you take the derivative of this with respect to x, derivative of this with respect to y, then back up at the level of little f, you would have had the mixed partials, and the mixed partials would be equal. Okay, so that means there is going to be this anti-gradient, and I'll show you how to do that. All right, just some terminology. You have simple closed curve and not simple closed. So if it intersects itself more than once, it's not a simple closed curve. Okay, the two curves above are not simple closed curves. Okay. All right, and we have connected regions, simply connected regions. So there's no holes in them, there are no breaks or gaps. So-called simply connected region. All right, so we're ready to get started. Okay, so 16.3, we had to do 3 to 21. And most of it's pretty computational, shouldn't be too bad. Yeah, I forgot if I showed these to you or not, but I'll show you again anyway. Say, determine if you have a conservative vector field, and if so, find the anti-gradient, find little f such that capital F is del F. 9, 11. 15, 17, 19, 21. Now, they snuck in some three-dimensional capital Fs. Okay, we haven't learned yet how to determine if a three-dimensional vector field is conservative, but they're just telling us ahead of time that it is conservative. We can find an anti-gradient. That'll be like problem 15. Okay, and we're asked to find such a function. And I think 17 is like that also. Okay, so here we go. Okay, problem 3. Capital F of xy is xy plus y squared I plus x squared plus 2xyj. Okay, like I said, once in a while I have to put the I in and j just to remember that's there, but most of the rest of the time I switch to angle braces. Okay, find the partial of p with respect to y. That's very easy. X plus 2y. Find the partial of q with respect to x. 2x plus 2y. Okay, are they equal? No, they're not. So therefore, f is not conservative. Okay, this is dot, dot, dot. You remember dot, dot, dot means therefore in logic, if you've never seen that before. Therefore, dot, dot, dot. So F is not conservative. So the problem's finished. I don't have to find an anti-gradient because it doesn't exist. I will not be able to find such an anti-gradient. Okay, so find a partial of P with respect to Y. Find a partial of Q with respect to X. Go ahead and put it on your next cheat sheet for the last test, not for this Thursday's test. All right, so that was a little bit too easy. So of course it's harder if we have a conservative vector function, like 5. Okay, so F is, and as you can see, I didn't write I and J. I just write it quote unquote once in a while. Okay, so this is P, this is Q. So take the partial of P with respect to Y. Okay, and that looks like a product root. So first function, y squared times the derivative of the second with respect to y, it'd be e to the xy times an extra x. Plus second function, e to the xy, times derivative of the first, which is y squared. Okay, and I cleaned it up a little bit. Factor out the e to the xy, xy squared plus 2y. Now the partial of q with respect to x. First function, second function, product root. First function, 1 plus xy, times the derivative of the second with respect to x. It'll be e to the xy times an extra y. Plus second function, e to the xy, times the derivative of the first with respect to x. That's nothing, and that will be y. Okay, and if you clean it up a little bit, I factor out the e to the xy. That's going to be distribute here, y plus xy squared plus y, or 2y plus xy squared e to the xy. Okay, so partial of p with respect to y equals the partial of q with respect to x. Therefore, f is conservative. So I can find an anti-gradient. Okay, I can find a little f so that the gradient of little f is capital F. Okay, so how do you do that? Right, so that means this is going to be fx. This is going to be fy. If this is the answer to a gradient problem, that's fx, that's fy. If there was a third component, it'd be fz, partial with respect to z. So fx is this, y squared e to the xy. So what I do now is anti-differentiate. Okay, and normally it's too tedious to keep writing the integral signs. We'll just go right to it. Okay, so don't write the integral symbols. Just say to yourself, I'm going to integrate with respect to x, which means y is constant. So the integral will be the same thing, e to the y squared, e to the xy, and then the chain rule in reverse. Okay, so what do I mean by the chain rule in reverse? If I were to differentiate this thing with respect to x, then I'd multiply by an extra y by the chain rule, right? Since I'm integrating, I divide by an extra y. So I have y squared divided by y, e to the xy. Okay, so this part here is y e to the xy plus, and this is new, plus g of y. I could have another function here that only has y's, it would still work. So right now, this is my little f. Quick double check. What's the derivative of this thing with respect to x? So the derivative with respect to x, I better get this thing. So what's the derivative? Where'd it go? This derivative with respect to x is the same thing times an extra y by the chain rule. Y squared e to the xy, correct? And then this thing, I don't care how many y's it has. I'm gonna have y squared, y cubed, square root of y, ln y, tangent y, inverse sine of y, whatever. It doesn't have any x, so its derivative with respect to x is automatically 0. So this works, agreed? The derivative of this is going to be y squared e to the xy. So that qualifies as fx for the gradient part. Okay, one more time. Derivative of this is the same thing times an extra y if I differentiate with respect to x. Okay, and the derivative of this, as long as there's no y's, it can be completely complicated. As long as it only says y's, the derivative with respect to x is 0. So that matches. Now you take this thing and differentiate with respect to y. You're basically kind of going up and down, anti-differentiate, differentiate, anti-differentiate, differentiate. Okay, differentiate with respect to y. So the derivative of this is g prime of y. That's easy. This one, derivative with respect to y, product root. So first function y times derivative of the second, derivative of e to the xy is e to the xy, times the derivative of xy with respect to y would be an extra x, plus second function, e to the xy, times derivative of the first. Derivative of y is just 1. Okay, so I have this thing. xy, e to the xy, plus e to the xy, plus g prime of y. Okay, and I factored out the e to the xy. I have 1 plus xy, e to the xy, plus g prime of y. Okay, so that's fy, and that has to match q, because if this is the result of the gradient, that has to be fx, that has to be fy. So fy has to be 1 plus xy, e to the xy. what do I have? I have 1 plus xy e to the xy plus some g prime of y. Well, in order for it to match what I have there, I just want g prime of y to be 0. That's nice. So I just set that equal to 0. So the derivative of what function of y is 0, a constant. So g of y is k. And in this section, Mr. Stewart uses k instead of c. They're really the same thing. I guess when you're doing this operation, I guess they want to reserve, blah, blah, blah plus c for calc 1 and calc 2. But now that we're in calc 3, you got to use k, I guess. It's really the same thing. All right, so final answer, little f of xy is y e to the xy plus any constant k. Okay, so just like in calc 1 and 2, plus c plus a constant, this can be 2 pi, a million, square root of 2 over 2, anything you feel like, it'll work. So here's the anti-gradient of this vector, i.e. the gradient of this comes out to be this. And you can always double check it. Okay, the gradient means the vector fx, fy. What's the derivative with respect to x? Well, same thing times y, so y squared e to the xy. What's the derivative with respect to y? I'm too lazy to show it again, but if you do the product rule the right way, it does come out to be that. And of course, the derivative of any constant is 0. Okay, so just like before, you can have any constant that you want here. This is like the plus c that you did in calc 1 and calc 2. Okay. All right, so that's what we're up against. Okay, number 9. Okay, capital F, y squared cos x plus cos y, 2y sine x minus x sine y. So this is P, this is Q. Okay, keep in mind the vector R is a position vector. So whatever you see here will be x, this will be y, and then the last one will be z. That's not true for F. F is not necessarily a position vector, so we call it P and Q. So take the partial of P with respect to y. So derivative with respect to y, 2y cosine x is constant, minus sine y. Take the partial of Q with respect to x. Derivative with respect to x, 2y cosine x minus sine y. And these are equal, therefore F is conservative. So I can find an anti-gradient of this vector function, and they ask you to find it. Okay, so how do I do that? So I set this equal to fx, this is fy, and then I do my up and down. I anti-differentiate, differentiate, anti-differentiate, differentiate, and so on. Okay. So here we go. So I start with fx, y squared cos x plus cos y. Integrate with respect to x. Normally, we don't write the integral symbol. It's going to take too long. Just write it f of x, y. So integral with respect to x, that's constant. Integral of cosine x is sine x. Integral with respect to x, well, that's constant. So x cosine y. Once again, plus some g of y. This can have a whole bunch of y's. Don't worry, we didn't don't. This can say y squared minus y cubed divided by square root of y plus ln y minus inverse tangent of y. The derivative with respect to x is 0. Okay, now take this thing and differentiate with respect to y. So go back down, anti-differentiate, differentiate, and so on. So derivative with respect to y, 2y sine x. Derivative of this, derivative of x cosine y is negative x sine y. Okay, and plus some g prime of y. Should be a plus g prime of y. Okay, that has to match this, 2y sine x minus x sine y. What do I have? 2y sine x minus x sine y plus g prime of y. So once again, that's the same as that, which means g prime of y has to equal 0. So the derivative of what function is 0? A constant. So g of y is a constant. And there we go. So final answer, the anti-gradient little f, it's a scalar function as opposed to a vector function, right? Vector function has components and has a direction. So capital F for vector function, little f for scalar function, y squared sine x plus x cosine y plus k, final answer. That is the anti-gradient of my original function, i.e. the gradient of this function is this. It's kind of like in Calc 1 when you started doing derivatives, you did antiderivatives. Anti-differentiate, say, I wonder if I did the answer correctly. Take the derivative and you just get that back. All right, so this is the anti-gradient. Again, don't quote me on this. I'm not sure if anti-gradient is a real word, but you get the idea. Okay, so before we had a little f and we found the gradient. Now we're going backwards. Okay, here's the result of a gradient. Come up with the anti-gradient. Okay, and we can check what's the gradient of this. So this, what's the derivative with respect to x? Y squared cos x, there it is, plus cosine y. That's correct. And the derivative of constant is 0. And what's the derivative with respect to y? 2y sine x. Yep. And the derivative of this is negative x sine y. Yep. And of course, the derivative of k is 0. So we know we did it right. Right. Now, problem 11, variation on the theme. They showed you a vector field, capital F, determined by 2xy and x squared. Okay, don't worry about drawing it. Okay, although some of you in Calc 2 did this. If you took me in Calc 2, you drew stuff like that, right? The direction arrows and all that. So you can do that with this vector field. Okay, they show you 3 curves that start at 1, 2, and then at 3, 2. Okay, so you can go like that, you can go like that, or you can squiggle and go like that. Explain why the integral of f dot dr has the same value for all 3 curves. So it has to be a conservative vector field. And then what is this common value? Okay, so here we go. So it's 2xy x squared. So what's the partial of p with respect to y? Derivative with respect to y? 2x. What's the partial with respect to x? 2x. They're the same. Therefore, f is conservative. Therefore, you have path independence. So it doesn't matter which path you pick. So those 3 curves that I showed you, they're all going to give you the same value. What is that value now? Okay, so let's find the anti-gradient, little f. So fx is 2xy. Integrate with respect to x squared y plus some g of y. Differentiate with respect to y, x squared plus g prime of y. And I have to set it equal to x squared. And very conveniently, and that happens a lot, that means g prime of y is 0, which means g of y is equal to k. So my f of xy is x squared y plus k. But just like in Calc 1 and 2, the easiest anti-gradient to pick is the one where k is 0. So just use x squared y. Okay. You're allowed to pick any anti-gradient. I'll just pick x squared y. So now I'm going to employ the fundamental theorem of calculus for line integrals, which was the first thing that I showed you in this section. Okay. So I find a anti-gradient, del f dot dr, f of r of b minus f of r of a, which means plug in the ending point, plug in the beginning point, and just subtract to find the value of the integral. All right, so my anti-gradient is x squared y plus k, just pick x squared y. All right, so it says you're going from 1, 2 to 3, 2. This is completely the multi-variable, multi-dimensional analogy to integral from a to b of f of x dx. Integrate capital F of b minus capital F of a, just subtract. Completely analogous. So find the anti-gradient. Here it is, x squared y. Plug in the ending point, 3, 2. So plug in 3, 2. It's 9 times 2. Minus plug in the beginning point, 1, 2. So 1 times 2 is 2. So 18 minus 2, final answer is 16. And there we go. All right, so that's that. All right. Now 13. Find a function little f such that capital F is equal to del F. Aha, that automatically means you have a conservative vector field, whether you have a 2-dimensional or a 3-dimensional vector. Okay, now if it's 2-dimensional, we know how to find if it's a conservative vector field, right? This thing, page 1090, partial p with respect to y equals partial of q with respect to x. As you might guess, it's a little bit more difficult if we have p, q, and r. We won't learn that rule now, but we'll learn it in a future section. Of course, it has to be pretty soon. There aren't that many sections left before we're done with the class. Okay, so how do I do this? I will show you what, 13. So capital F is x squared y cubed I plus x cubed y squared j. And C is R of t is t cubed minus 2t, t cubed plus 2t between 0 and 1. All right. I'm going to translate this into points. Okay. T is 0. Plug in 0, 0, 0, 0, 0, 0. Plug in 1. 1 minus 2 is negative 1. 1 plus 2 is 3. So we're going from 0, 0 to negative 1, 3. Okay. Now, just like the previous problem, right? If we have path independence, which means we have a conservative vector field, it doesn't matter what path you pick. So I don't care if we're going by this path. All I'm going to do is plug in negative 1 and 3 and plug in 0, 0 once I find the anti-gradient. Okay, they already told us this is a conservative vector field. Okay, that means fx is this, fy is this. Okay, so not f of x, sorry. It should be f of x comma y, 2-dimensional, of x, y. Okay, so integrate with respect to x. This is fx, right? So that's 1/3 x cubed y cubed plus g of y. Okay, again, this is supposed to be fx, this is fy. So integrate with respect to x, x cubed over 3 or 1/3 x cubed y cubed plus g of y. Now differentiate this thing with respect to y. So 3 cancels 1/3 x cubed y squared plus g prime of y. And that's supposed to equal x cubed y squared. So once again, that forces g prime of y to be 0. That means g of y is k. I can pick any anti-gradient. So the easiest anti-gradient to pick is just 1/3 x cubed y cubed. Okay, quick double check. What's the derivative with respect to x? That, x squared y cubed, right? What's the partial with respect to y? X cubed y squared. Okay, yeah, we're taking partial derivatives. Maybe I neglected to say it, and some of you may be wondering, are these the same as partial derivatives? Yes. Okay. It's shorter to say fx and fy, but those, yes, it's a partial of f with respect to x, partial of f with respect to y. Okay, so here's my anti-gradient. Therefore, all I have to do by the fundamental theorem of calculus for line integrals, just plug in the ending point, plug in the beginning point, and that'll be my answer. Okay, so I plug in what? Negative 1, 3. So negative 1 goes there, 3 goes there. So that's negative 1/3 times 27 is negative 9. Plug in 0, 0, you get 0. So the answer is negative 9. And yes, it's perfectly fine for an integral to come out to be negative 9. Right? That was true even in Calc 1 and Calc 2, right? Integrals can come out negative. So that means a signed area, right? The signed area is allowed to come out to be negative. Okay. Yeah, anybody who joined late, go ahead and put it in the chat and I'll get you eventually. Okay, now for 3-dimensional variety. So 17. So this gets a little bit harder. F of x, y, z is y, z, e to the xz plus e to the xz plus xy e to the xz. Along the curve, r of t is t squared plus 1i plus t squared minus 1j plus t squared minus 2tk. T goes from 0 to 2. Okay. Now, and again, I got lazy. I decided not to write the I, J, and K and do the angle braces. Okay, they're already telling me that this is a conservative vector field. Now, right now, we don't have any tests for a three-dimensional vector for a conservative vector field, except they already told us that it's a conservative vector field. Okay. That means I'll figure out the starting point and the ending point. How do I find out? Plug in 0, plug in 2. And remember, that is x, y, z. R is the position vector. Remember, R is a position vector. So this is x, this is y, this is z. Maybe for emphasis, I'll put this again. That's x, y, and z automatically. That's not true for F. This is not necessarily a position vector. So we would normally just call them P, Q, and R. All right, so what's my starting point? Plug in 0. 0 plus 1 is 1. 0 minus 1 is -1. And 0 minus 0 is 0. So I'm starting at the three-dimensional point in space, 1, -1, 0. Right? So that means from the origin, you go 1 out, 1 left, and don't go anywhere up or down. Okay, and I'm going to 2. Plug in 2. 2 squared plus 1 is 5. 2 squared minus 1 is 3. 2 squared is 4. 4 minus 4 is 0. Okay, so in space, I'm going from 1, -1, 0 to 5, 3, 0. And you can go in any path. You can go straight there. You can squiggle around all over and end up over here. Okay, you'll get the same answer if you have a conservative vector field. Okay, and yes, this leads to all the conservation laws in physics. Conservation of energy, conservation of mass, sometimes conservation of charge, conservation of momentum, conservation of angular momentum, and so on. All the conservation laws in physics. Okay, here's our first example of doing this up and down when you have 3 variables, x, y, and z. It's pretty much the same thing, but you just have to do it one more time. So it's a little bit more tricky. All right, so this is fx, this is fy, this is fz. Okay, so if this is fx, I now integrate with respect to x. So f of x, y, z. yz e to the xz. Okay, so what do I have here? Something's not right. I don't like what I have. Check it again. Yz e to the xz. I'll just go with it for now. And this might be one of those where I have to correct myself because I messed up. But for now, let me just go with fxyz is y e to the xz plus g of yz. Let's see. Somehow I'm not really happy with that. Let me just finish the details. I don't think this is correct. So this may be one of those that I messed up again, but let me at least show you the theory behind it. Okay, so if I integrate with respect to x correctly, which I don't think I did. Okay, but now you have to put g of y and z. Okay, before I had g of y, but this can have a whole bunch of y's and z's. Okay, the derivative with respect to x won't matter. It's still going to end up being 0. Okay, so now I differentiate with respect to y. So if I differentiate with respect to y, I'll just have e to the xz. Okay, that's good. That works. Plus g of y, g sub y. Z is going to drop out, but I have g of y. Okay, and then I look at what I have here. I have e to the xz. E to the xz plus g of y, g sub y is e to the xz. That means g of y is equal to 0. There's this g of yz does not have any y involved, but it still might have h, which means f of x, y, z is now my y e to the xz plus h of z, some function of z. Okay, now I differentiate with respect to z. Fz is the same thing times an extra x, xy e to the xe, plus h prime of z. Okay, that's supposed to equal xy e to the xz. And once again, that means h prime of z is 0. Okay, so my anti-gradient f of xyz is y e to the xz. Whoops, where'd it go? Yeah, here we are, y e to the xz. Okay, and let me double check. If I differentiate with respect to x, I multiply by an extra z. Yeah, that's correct. Oh, I see what I did. Yeah, I actually didn't mess up. I have to check my explanation. Okay, and what's the derivative with respect to y? I just drop it, e to the xz. And then what's the derivative with respect to z? It's the same thing times an extra x. So xy e to the xe. Yeah, it works. Yeah, getting back to my explanation here. Yeah, if I were to differentiate with respect to x, I'd multiply by an extra z. This expression right here. Differentiate with respect to x. You put the same thing times z. Right, so when I integrate, I divide by z. That's right, which now leaves me with y e to the xe. So yes, I think I'm good. Okay, and double check, what is the derivative with respect to x? I'd put the same thing times an extra z. Yeah, okay, we're good. So the anti-gradient is y e to the xz. H prime of z is 0. So again, you can have any constant, but use y e to the xz. So we've determined the gradient of little f is indeed, that's fx, that's fy, that's fz. So the fundamental theorem of calculus now says to find the integral of f dot dr, I just do f of my ending point, 530, minus f of the beginning point. Yeah, this is integral along C of f dot dr. The function dot with a tiny change in arc length. Okay, so plug in 530, 530, 0 here makes that 0, e to the 0 is 1. So y is just 3, so it's 3 minus f of 1, negative 1, 0. Put a 0 there, that's 0. So again, it's e to the 0, which is 1. So I just have the y, which is negative 1. So 3 minus a negative 1, and my answer is 4. Okay. Okay, then 19. Show that the line integral is independent of path and evaluate the integral. Okay, the way they write it like this, that's like f dot dr. Okay, I'll write it in the book. This is integral of f dot dr, which is p dx plus q dy. So f is the vector pq, dr is dx dy, or in 3D, dx dy dz. Okay, so in other words, that 2x e to the negative y, that's my p. The 2y minus x squared e to the negative y, that's my q. And evaluate the integral. Okay, so that shouldn't be too bad. Okay, 2x e to the negative y dx, that's p. 2y minus x squared e to the negative y dy. Okay, so show that you have a conservative vector field. Find a partial of p with respect to y and a partial of q with respect to x. Partial of q with respect to x. I'm actually writing this first for a reason. It's to set you up for the next section. Okay, so derivative with respect to x, that's nothing, minus 2x e to the negative y. Derivative with respect to y is the same thing times negative 1, negative 2x e to the negative y. Yeah, if it looks like I'm writing it backward, it's to set you up for the next section, because the next section they actually write it like this. Therefore, f is conservative. So I can find an anti-gradient. So here we go. So again, this is fx. Fx is 2x e to the negative y. So integrate with respect to x squared e to the negative y plus g of y. Differentiate with respect to y. So same thing, times -1, negative x squared e to the negative y plus g prime of y. And now here's our first case where it's not just going to turn out to be 0 for g of y. G of y is 2y minus x squared e to the negative y. We have negative x squared e to the negative y. I can barely show you both at the same time. That has to equal that. So there's a negative x squared e to the negative y, right? I don't have the 2y. So that forces g prime of y to be 2y. Okay, one more time. That has to match that. I see the negative x squared e to negative y. So in order for them to match, g prime of y has to be 2y. So if g prime of y is 2y, that makes g of y y squared plus a constant. So here's our first instance where the g of y is not a constant. So my f of xy is x squared e to the negative y plus y squared. There's my anti-gradient. Okay. Double check. What's the derivative with respect to x? 2x e to the negative y. What's the derivative with respect to y? Negative x squared e to the negative y plus 2y. There it is. Okay, and then I'm all set. So evaluate the integral, and it says go from 1, 0 to 2, 1. So 1, 0 to 2, 1. Plug in 2, comma 1. So put a 2 here and a 1 here. So that's going to be 4 e to the negative 1 plus 1 minus plug in 1 and 0. So 0 there wipes that out. Put a 0 there, that's a 1. And that's 1. So it's 4 e to the 1 plus 1 minus 1. Final answer is 4 over e. Okay. All right. I'm just about done, folks. Quickly for 21, which is not really a problem. Suppose you're asked 21, you're asked to determine the curve that requires the least work for a force field F to move a particle from one point to another point. You decide to check first whether F is conservative, and indeed it turns out that it is. How would you reply to the request? So find the curve that requires the least amount of work. And by the way, yes, this is F dot dr. Sometimes this gives you work as a force times distance, as it is. How would you reply to the request? Well, we have a conservative vector field, so quite simply, it doesn't matter which path is chosen. Any path you pick would give you the same result. Okay. All right, so that's that. Let me do my focus thing, and then we will break. And I'm actually done with a section. Okay, so after the break, I will get started with 16.4, but I do want to leave you some time for questions and answers in preparation for the exam, if you have any. Because we're not having any questions and answer session next time, as you know. Okay, I'll sneak in that. It doesn't matter which path is chosen. And there we go. Okay, so I'm going to mark off that we're finished with 16.3. This is done. So after the break, I'll start 16.4, and then I'll take questions and answers if you have any. Okay, if anybody joined late, go ahead and put it in the chat, but we'll go ahead and break now into our usual 7:10. So let's see. Okay, yeah, I'll answer any question a little bit later, but let's break until 7:10. All right, folks, let's pick up where we were. So I'm going to do some of 16.4. I'll let you ask questions if you have any, and then we'll go from there because you won't get a chance to ask any questions for the test on Thursday, okay? So let's go back to sharing the screen. Okay, so 16.4 is on Green's theorem. And this is only in the plane. It's only in the XY plane. Sometimes it's called Green's theorem in the plane. I'll mark down 16.4. But I know I won't finish it, so I'll pick up with 16.4 when we come back on Tuesday, the 27th. Okay. Now, a question was brought up before the break. Yes, for a three-dimensional vector, the capital F, P, Q, and R to find the anti-gradient. Yes, this was Fx, Fy, and Fz. Okay. That's not a guarantee. We have to find the anti-gradient. But if there is such a function, capital F, then yes, P, Q, and R, this would be the Fx, this would be the Fy, this is the Fz. Okay, so that was asked in the chat. And I think I'm caught up now.
I had another question, Professor.
Okay.
So as far as like the breakdown of these problems, so you're taking f of x, y, then you take the integral of p, basically, or fx, right?
Correct.
And then you take that integration answer and take the derivative with respect to y.
Right. You just go to the next letter, as it were.
And then the next letter you would take the integral of that to with respect if it was z. So
So you start with fx, integrate, then differentiate with respect to y, integrate, and differentiate with respect to z. So you just kind of go up and down the process. If you're talking about 17.
Right. Yeah. Well, I'm talking about basically like the general process.
Mm-hmm. Yeah, I'm taking the most general case where it's the three-dimensional vector, which is the only one I did here. We'll do more when we get to a future section, but
okay.
Yeah. So if you look over here, and of course, don't worry about this for this Thursday's test, obviously. But yeah, integrate with respect to x, differentiate with respect to y, right? Integrate with respect to y, differentiate with respect to z. That's sort of what's going on here in this one example.
Okay. All right.
Okay.
Cool. Thank you.
All right. Okay, 16.4, Green's theorem in the plane. I'll show you the theorem, then I'll talk about it. It basically says that C be a positively oriented, piecewise smooth, simple closed curve in the plane. So it has to be a simple closed curve. Let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region contains D, then you have this. Okay, so first of all, it's a closed region. Positive orientation is clockwise, just like in trig, right? If you start off with 0 to the right and then you go clockwise. So this is considered a positive orientation. If you look at the way the arrows are going overall, you're going counterclockwise. And negative orientation will be clockwise. So see, if you follow the tracing of the arrows, right? And then you have it. Okay. And one way you can think about it is for positive orientation, the interior is always on your left. Is that correct? So if you walk along A, see where those arrows are? The inside is always on your left. For negative orientation, the inside would always be to your right. Is that correct? Yeah, and a side note, you may notice in typical track and field, when you run track and field, it's almost always this way, isn't it? Where the inside is to your left. You never run the other way. Why? That's just what we all decided to do. Is that correct? When you run track, when you run around track, right, the interior is always on your left, isn't it? Okay. And what's wrong with running the other way? Nothing. I guess that's just not what we do. Okay, so positive, negative. Okay, this says to evaluate the integral, you have a choice. You can either do the f dot dr, the p dx q dy, or you can switch it to a double integral of the partial of q with respect to x minus the partial of p with respect to y dA. Switch it to a double integral. Okay, we won't prove it, we'll just state it. The text goes over a little bit of a proof, you can look at it or not. But which one is usually easier? It depends on the functions, but normally it's easier to do a double integral. I know that sounds counterintuitive, but you're really just doing one double integral. Sometimes when you have this, especially if they're divided into different pieces, it can get long. Okay, now that's even like the one quiz that we had last week, but I didn't have you evaluate each of the 4 line segments. Okay, you'll have to actually do it in this instance. Okay, so integral along C of p dx plus q dy, and this is another way of what they're saying is f dot dr, which can also be thought of as work. In fact, F is used for force also, force times a little change in distance. So you sum it all up, you have work, F dot dr. So F is PQ or PQR, dr is dx dy. Okay, partial of Q with respect to X minus partial of P with respect to Y. Okay, so we can either do this or this. Now, one thing you'll notice right away is that looks like something familiar. For a conservative vector field, partial of P with respect to Y equals the partial of Q with respect to X, which means if they're equal, what would this quantity be? 0, because you have a conservative vector field, which means you'll be integrating 0, integral of 0, 0, which means, do you think most of the problems in this section are going to be conservative? They will not be in general, because it's too easy, right? If you have a conservative vector field, then that is going to be the same as that. So if you subtract, you're integrating 0, and it's too easy to just integrate 0. So the vast majority of the homework problems in this section, you will not have a conservative vector field. We will not be able to find that anti-gradient. Okay, and side note, sometimes you'll see a little circle. See where it has integral along the curve of p dx plus q dy? Sometimes you see a circle, and I'm not sure if you can see that. Sometimes you see an arrow in a clockwise direction, showing that's the positive orientation. Okay. So if they tell you to go clockwise, then it's going to be a negative orientation. So the answer is going to be the opposite or the negative of what we want. Okay, and there's even other notations. See, they have a D, number 1, partial of Q with respect to X minus partial of P with respect to Y, dA. And then is integral, and they look like the partial D of P dx plus Q dy. So that's another notation. I don't like it myself, so I don't use it. Okay, and I don't even do those circle things. So see the circle, it just tells you you're going in a curve, just to remind you that you're doing it. And then that little arrow is also there. So I might use it or I might not. Okay. Right. Now you can see what's happening. This is where the field gets really, really rich. Okay, sometimes too rich, where the integrals just get really bad. So again, we've come a long way from integral just along the line segment from A to B. How about integrating along this thing or this thing? And now we actually have a choice. Would you rather integrate along the curve or along the interior? In this case, the interior looks like I would switch the polar coordinates, right? Okay, so I'll do some problems, but that might depend on how far you guys want to go. So let me show you the problems that we have on top. So we quote unquote only have 1 to 13, odd 17, but skip 11. I originally wanted to do 11, but I think it got too long. So skip that. Okay, 16.4, 1101. Evaluate the line integral two methods, directly and using Green's theorem. Okay, so number one, integral along C of y squared dx plus x squared y dy. C is the rectangle with vertices 0, 0, 5, 0, 5, 4, 0, 4. Okay. I think this is the only one that I did the whole thing. So yeah, that's like p dx plus q dy. Right. So the normal positive orientation is you're going counterclockwise. So I did the 1 arrow, 2 arrows, 3 arrows, 4 arrows, curve 1, curve 2, curve 3, curve 4, right? So to evaluate all the way around, I have to figure out all 4, which is quite a bit of work. No question about it. Okay, so this is y equals 0, x going from 0 to 5. C2, x is 5, y goes from 0 to 4. Okay, and now this is a little bit tricky. You have to go this way, which means this is the equation y equals 4, but I have to say x is going from 5 to 0, not from 0 to 5. That's key. Okay, look at the arrows. You're going this direction. So in this direction, I'm not going from 0 to 5. I'm going from 5 to 0. Likewise, from C4, the 4 arrows down. Okay, that's the equation of x equals 0, but y is going from 4 to 0. Now, how come I didn't do the arrows thing here? Well, because we're comfortable going from 0 to 5. And we're comfortable going from 0 to 4. Okay, it's a little bit unusual to go from 5 to 0, but that's what's happening here. And here, y is going from 4 to 0. So you have to have it in that fashion. Okay, so the integral along C is the integral along C1 plus C2 plus C3 plus C4. Okay, so I have to figure out all 4 of them. All right, so fortunately C1 is 0. Let's see why. Integral of y squared dx. So y is 0. And y is 0 here. So I'm integrating 0. So 0, right? Plug in 0 for y here and here. That wipes everything out. First integral is 0. Okay, C2. Y equals 0 to 4. And the equation is x equals 5. That means dx is 0, right? The little change in x, there is no change in x. So this part is 0. Plus x squared y dy. That's 5 squared y dy. And I'm integrating from 0 to 4. 25. So that's 25 y squared over 2 from 0 to 4. 25 times 8, 200. So C2 is 200. C1 was 0. C3. Okay, again, I have to go from 5 to 0. I'm going from 5 to 0. Let's see, x squared y dy. There is no change in y. Right? Dy, remember, is a tiny little delta y. There is no delta y, so that's 0. Okay, y is equal to 4 up here, so that's going to be 16. So it's the integral of 16 dx, and you have to go from 5 to 0. We are going in this direction. So it's 5 to 0. So 16x from 5 to 0, plug in 0, you get 0, minus plug in 5, so that's negative 80. Okay, finally C4, x is 0, dx is also 0. Okay, so if x is 0, that's 0, dx is also 0, so this whole thing is 0. But yes, ordinarily I would have to integrate backwards again from 4 to 0, but dx is 0, there is no change in x, and x is 0 here, so that wipes that out, so I have 0. Therefore, final answer, the integral along C is the integral of C1, which came out to be 0, plus the integral along C2, which was 200, plus the integral along C3, which was negative 80, plus the integral along C4, which was 0, grand total of 120. So we had to do 4 integrals. Part B, instead, do 1 double integral. I think you'll find out that that's generally easier. So what did I do? So here's Green's theorem, put it on your next cheat sheet, not Thursday's cheat sheet. So I did the left side, integral of p dx plus q dy, kind of long. The right side doesn't look so bad. It will not come out to be 0. Most of these aren't going to be 0. That's too easy. So the double integral of partial of q with respect to x minus the partial of p with respect to y. Okay, partial of q with respect to x is 2xy. Partial of p with respect to y, 2y. I did not did 0. It is not conservative. Okay, and I integrate. Our favorite is dy dx. Y goes from 0 to 4. X goes from 0 to 5. I think you'll agree this is much better, even though it's a double integral. It's way faster than doing all these 4 integrals plus analysis. All right, so let's see, integrate with respect to y. So xy squared minus integrate with respect to y squared. Y goes from 0 to 4. Plug in 4 here, that's 16x minus 16 dx, integral from 0 to 5. So that integration is 8x squared minus 16x from 0 to 5. Plug in 0, you get 0. Plug in 5. 8 times 25 is 200. Minus 16 times 5 is 80. Answer is 120. Same answer both ways. As you can see, it's long. And coincidentally, but maybe not so coincidentally, we got here 200 minus 800. Look at what we had here. We had 0, 200, negative 80, and it came out to be 0, right? For the last one. Can't find it. Yeah, 0. So same answer. All right, so that was number 1. You do number 3. I won't go that much longer. Now look at the language for number 5. Use Green's theorem to evaluate the line integral along the given positively oriented curve. So that means they're giving you a choice. Do you want to do the left side or the right side? Now look at number 5. Again, it's a triangle. It's just different function. And they give you a rectangle again. So it's the same thing. I can either do these 4 integrals and do all the analysis like this, or I can just do a double integral. Can you guess which one I prefer? The double integral, especially when you have a rectangular region. That's going to be way better, right? So I'm not going to break down to C1, C2, C3, C4. I'm just going to go with this because I like that better. Okay, so this is P dx, Q dy. So I'm going to do the right-hand side. Partial of q with respect to x, 2e to the x. Minus partial of p with respect to y, e to the x. Okay, and this time I decided to go dx dy just for variety's sake. You didn't have to. By Fubini's theorem, you can switch it, right? And that's a reminder for the test. For Fubini's theorem, if all you have is constants, you can change the order any way you want. Our favorite is dz dy dx, but you can do dx dz dy or any of the others. Okay, well, 2e to the x minus e to the x is just e to the x. So integrate e to the x. Oh, yeah, this thing does not involve y. So take out the length of the interval of y, which is 4. So 4 integral from 0 to 3 of e to the x dx. Integral of e to the x is itself 4e to the x. So plug in 3, plug in 0. So 4 times e cubed minus 1, and that's my answer. Okay. All right, I was going to just do one more and then I'll stop. And then you can ask me questions pertaining to the test. 9. Integral along C of y cubed dx minus x cubed dy. That's p dx minus q dy. C is a circle, x squared plus y squared equals 4. Whoops, here we are. Okay, this is P, this is Q. Maybe I'll write it. All right, so I think we agree we'd rather integrate along a circle. And since it's a circle, I'm probably going to switch the polar coordinates. So x squared plus y squared equals 4 has a radius of 2. So partial of q with respect to x, negative 3x squared. Partial of p with respect to y, negative 3y squared. dA. Very nice polar coordinates, right? So factor out the negative 3. I have x squared plus y squared, and x squared plus y squared is r squared. And then in polar coordinates, r, dr, d theta, which is a nice little mini review for the test also. So it's a nice little side effect of doing new stuff as we review the old stuff. And that's easy. R goes from 0 to 2, theta goes from 0 to 2 pi. So I have r cubed, constant, 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 constant. There's no theta involved. So shortcut, just take out the length of the interval, which is 2 pi. So negative 3 times 2 pi, integral from 0 to 2 of r cubed dr. So that's negative 6 pi, r to the 4th over 4 from 0 to 2. Plug in 0, you get 0. Plug in 2, 2 to the 4th is 16, divided by 4 is 4. So negative 6 pi times 4, negative 24 pi. All right, that's it. I'm just going to show you. I started doing 11 and I decided it's too long. Okay, so you don't really have to look at it, but I got started with it. Okay, and I even wrote down it's too long. Okay, plus I messed up. What else is new? Okay, so I got all this stuff and then it just got too overbearing. So I decided to just skip it from there. Okay. All right, so let me just do this focusing thing and then I'll let you ask questions pertaining to the test because you won't get a chance to ask Thursday. Then we'll pick up from here next Tuesday with where we were. So that and 9, and there we go. Okay, so I got in sum of 16.4. Why don't I just mark this off now? So that's Thursday. This would be like 16.4. Whoops, I got it in red. Switch my colors here. Well, it doesn't matter. 16.4 and maybe 16.5 next Tuesday. Okay, but again, none of this will be on Thursday's test. Thursday's test is exclusively on this stuff, right? 15.1 to 15.9. Okay. All right, so I will now let you ask questions. You can either unmute yourself or put it in the chat, but otherwise that's it. Let me look at the chat real quickly. Anybody join late? Put it in the chat right now. Let's see.
15.3, number 11.
Okay. Write some of this down. 15.3, 11, and any more? I'll check the chat, but you can also unmute. 15.3, 11. Okay, well, let me start with that. And then if I hear any more, feel free to put some more. 15.3, number 11. Okay, that one. Okay, so let me put that down. Let's see if I got some paper here. .311. Okay, double integral over the region D e to negative x squared minus y squared dA. And a semicircle, x equals, found that x equals radical 4 minus y squared. And the y-axis. Okay, so if I do a little bit of algebra, that's x squared plus y squared equals 4. If I solve it as x equals blah, 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 that means x has to be positive. So I don't have this. So I only have this region here. So this is the region in question. So if this is the region in question, how should I do my theta? Okay, so r is between 0 and 2. You can't say from 3 pi over 2 to pi over 2, that's backwards. Okay, you can say from 3 pi over 2 to 5 pi over 2, or you can start at negative pi over 2 up to positive pi over 2. I think that's preferred. So theta is going to be between negative pi over 2 and pi over 2. Okay, so I'm going to do double integral e to the negative x squared minus y squared. That's e to the negative parentheses x squared plus y squared. And we know that x squared plus y squared is r squared, right? So e to the negative r squared, and then r dr d theta. And r is going from 0 to 2. Theta, I'm going to say from negative pi over 2 to pi over 2. Fortunately, it's fairly easy because there is no theta here. Constant, 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 constant. Just take out the length of the interval. The length of the interval is pi. And yeah, that would have been the same thing if I went from 3 pi over 2 to 5 pi over 2. It would still be pi. But you can't say 3 pi over 2 to pi over 2 because that's backwards. That'd be actually going this way. All right, so take out the pi. That's the length of theta interval. And then, yeah, let me do the u substitution without doing the u substitution, 0 to 2. E to the negative r squared. Let's see, the derivative of negative r squared is negative 2r. So that means negative 2 inside, which means negative 1/2 outside. So if I did the u substitution, right, it'd be e to the u du. So the integral is e to the u, which is e to the negative r squared. Okay, so negative pi over 2, e to the negative r squared from 0 to 2 equals negative pi over 2. Plug in 2, you have e to the negative 4, minus plug in 0, you get 1. Okay, and technically that's correct, but we don't like the way it looks. Okay, that's a negative, and this number is smaller than this. So usually when you get this, turn it around. So this is positive, and this is positive. Pi over 2, 1 minus e to the negative 4th. Okay, so that's my answer for that one. So key thing here.
With that problem, could you go from 0 to pi over 2 and then just multiply it by 2?
Can I go from 0 to pi over 2 and multiply by 2? Okay, let me get back to that. Let me finish what I was going to say here. A reminder. So e to negative x squared minus y squared. Polar coordinates is the way to go here. That becomes negative r squared. Okay, r is going from 0 to 2. Theta is negative pi over 2 to pi over 2. Now, can I go from 0 to pi over 2 and double that? We're not sure. Okay, it depends if you have symmetry in the function from here to here, and that's not necessarily the case. For e to the negative r squared, I'm not sure if that's going to be true here. So yeah, you better not do it in that particular case. Okay, so yeah, just go from negative pi over 2 to pi over 2. And in this case, it comes out pretty easy. You can just take the length of the interval, which in this case was pi. So yeah. Okay, anybody else? I've quote unquote caught up, unless I see some others here. Okay, 15.2, number 51. 15.251. Okay, evaluate the integral by reversing the order of integration. Okay. 15.251. Integral from 0 to 1, 3y to 3. E to the x squared dx dy. Okay. And you can see we're in trouble here. You might recall from Calc 2, there's no easy way to integrate e to the x squared. So how do we do it? So this is x. X equals, y equals, y equals. So x equals 3y. You're probably more comfortable with y equals 1/3 x, right? Same thing. The slope is about 1/3. You go to x equals 3. Well, that's just somewhere here. This is the point 3, 1. How do I know that? I just plugged in. And y goes from 0 to 1. Okay, so type 2, this is the region in question. So x is going from 3y. Here's x equals 3y. We're more comfortable as y equals 1/3 x. Here's x equals 3. Y goes from 0 to 1. Okay, switch it around. So if I switch it around, y goes from 0 to 1/3 x, right? Y equals 0, y equals 1/3 x, and then x goes from 0 to 3, right? So that's what I'm going to do. It's the same function, but one more time. If I do dy dx, y goes from the lower to the upper. So y equals 0 to y equals 1/3 x, x goes from 0 to 3. Okay, so let me show you how that's going to work out now. E to the x squared dy dx. Y goes from 0 to 1/3 x. X goes from 0 to 3. Okay, now this is doable. The first integral is with respect to y. There is no y. So the integral is just the length of the interval. I have to watch out, integral and interval sound the same. So what's the length of the interval? 1/3 x minus nothing, 1/3 x. And then I get the x that I need to do my substitution. Okay. And this is length of interval. Okay. All right, take out the 1/3. I'll leave a space because I know I have to multiply something else. 0 to 3 x e to the x squared dx. Okay, switch colors here. What constant should I put here in order for the u substitution to work? If u equals x squared, du is 2x dx. So 2 here, which means 1/2 here. So it's going to be e to the u du. So it's going to be e to the u. Well, what is e to the u? E to the x squared. From 0 to 3. So 1/6. Plug in 3, you get e to the 9th. Plug in 0, you get 1. So there we go. 1/6 e to the 9th minus 1. Okay. Okay. Getting several others, so I'm going to have to write all these down. 15.6, 3 and 11. 15.7, 21. 15.9, 11. By the way, if the problem is too long, I may decide not to do it. Okay, 15.6, number 3. Okay, I have to close the chat so I won't be able to see it temporarily in case anybody has more problems. 15.63. And go from 0 to 2. And we'll go from 0 to z squared. Don't worry if you can't see it yet. I'll adjust it eventually. 0 to 2, 0 to z squared, 0 to y minus z. Two x minus y dx dy dz. Quick reminder, inside function and have the other two letters. So I see x, you're allowed to have y and z, that's fine. Next one, y, you're allowed to have z. Yes, the last one has to be constants. Okay, well, fortunately, these are all zeros, so that does make it nice. So 0 to 2, 0 to z squared, integrate with respect to x. So that's going to be what? X squared minus xy. X goes from 0 to y minus z, dy dz. Plug in 0, you get 0. Don't even bother to write it. These integrals get so long, 0, forget about it. So just plug in y minus z. So integral from 0 to 2, integral from 0 to z squared. So what do I have? Y minus z squared, right? Minus y minus z times y dy dz. Okay, so let's see how long this gets. 0 to 2, 0 to z squared. Okay, so what's that? Y squared minus 2yz plus z squared minus y squared minus a minus, so plus yz dy dz, assuming I did that correctly, which is no guarantee. I'm sorry, that's not y squared, it's yz. Again, if you do the setup correctly, I will give you most of the credit. Okay, I don't think you should be penalized if you know what's going on and you made, a simple algebra mistake. I make plenty of algebra mistakes, as you know. Let's see, that cancels out. Negative 2yz plus yz, so that's a negative yz, is that right? So integral from 0 to z, 0 to 2. Integral from 0 to z squared. Let me write it as z squared minus yz, right? dy dz. Okay, so if I integrate with respect to y, that's yz squared minus y cubed over 3. Okay, so I have to come up to do it. Integral from 0 to 2. So what did we say? Yz squared minus y cubed over 3. Integral of this is constant, so z squared y cubed over 3. Y equals 0 to z squared dz. This is really long, but you should be happy they're all zeros. It'd be much worse if, this was a 1 and that was a 7 and whatever. Okay, everywhere you see y, put z squared, and 0 gives me 0, so that's nice. So z squared times z squared, z to the 4th. Z squared cubed, z squared cubed, z to the 6th, 1/3, z to the 6th, dz. Okay, so z to the 5th over 5 minus 1/3, z to the 7th over 7 from 0 to 2. And to save time, I'm just going to put etc. You should be able to take the rest of that. Let's see if I get time to do the rest of the problems. Okay. 11. Okay, so they give me all that stuff. Z over x squared plus z squared. Oops, didn't write it right. x squared plus z squared. Y goes from 1 to 4. Z has one other letter, X has another letter. So Y should be last, correct? Goes from 1 to 4. Okay, then what do we have? Z goes from Y to 4, X goes from 0 to Z. Z equals Y to 4, that's allowed. Yeah, this is key. X goes from 0 to Z, that would not be allowed because Z would already be finished. Okay, so that means X has to come first. X equals 0 to Z. Z goes from 0 to, what was it? Z goes from Y to 4. All right, so that was a little bit tricky. If I switch it around, Z would already be gone. So X has to be first. Dx, dz, dy. Okay, this is going to take a while. So I'm afraid I'll have to stop that. Remember how to integrate something like that? It's going to be an arctan kind of thing. So it's probably going to be too long. So I'm going to have to say, etc. Of course, I have a big advantage. I'm the teacher. I get to say, etc. I don't want to do any more, but you guys don't have that option, obviously. Okay, but you might recall to integrate something like this, like 1 over x squared plus 1. That's an arctangent. Okay, but not quite. I have to do some factoring out there. Okay, so it's not likely that I'll have you do this entire thing. Maybe just a portion of it. Okay, so sorry about that. I know that doesn't really satisfy, but it's as much as I'm willing to do for that one right now. Okay, 15.7. You might think it's, I'm torturing you to have you try these long, difficult problems, but you want to try some harder problems, even if they're not necessarily going to be in a test. You want to see a bad problem, how bad some of these problems get and how long this could be. It's doable, but I can tell it's going to be quite a while to do this one problem. So sorry about that. 15.721. .721. Okay. So, triple integral over E of x squared dv. I wonder if I already did this one, in which case I'll just show you what I had originally. Okay, above the plane z equals 0, so x squared plus y squared equals 1. The plane z equals 0, which means above z equals 0. And z squared equals 4x squared plus 4y squared, which is the same as z squared equals 4r squared, or z equals 2r. Did I show you this one before? Check. Presented that. Because if I did it, then I'll just show you that again. Maybe I didn't. .21, I did not do. All right. Okay, so let's get back to where we were. So we have our cone, z equals 2r. And inside the cylinder, x squared plus y squared equals 1. Okay, so we know what that looks like. So this is r equals 1, right? All right, so we're inside here. We know that r is between 0 and 1. Theta is between 0 and 2 pi. So let me check what I have here. It's below something, right? Below the cone, right? So we're starting at 0 and we're going to 2r. So z is going from 0 to 2r. So z squared equals 4x squared plus 4y squared is z squared equals 4r squared. Take the square root, z equals 2r. It's above, so I don't need to do plus or minus. Okay. So triple integral, z goes from 0 to 2r. And we're bounded here. That's my unit circle. So r is going from 0 to 1. Theta is going from 0 to 2 pi of x squared. X is r cosine theta. So r cosine theta squared r dz dr d theta. Okay, there's a theta. There's an r. So I can't just throw everything out. Okay. 0 to 2 pi, 0 to 1, 0 to 2r. So it looks like I have r cubed cosine squared theta dz dr d theta. Well, at least when I integrate with respect to z, there's no z. So it's just going to be the length of the interval, which is 2r. So I'm going to go from 0 to 2 pi and go 0 to 1 of r cubed cosine squared theta times the length of the interval of z, which is 2r dr d theta. And let me just clean this up right now. That's going to be 2r to the 4th cosine squared theta. Okay, I'm about to turn the paper over, so let me quickly do my focusing thing. Whoops. Well, should just come down this column here first. And then all of this. Okay, so I might have to et cetera this. Let's see, 2r to the 5th over 5 cosine squared theta. R goes from 0 to 1. Theta goes from 0 to 2 pi. D theta. Plug in 0, you get 0. Plug in 1, you have 2/5. Okay, do you remember how to integrate this? Change it to 1 plus cosine 2 theta over 2. And then again, save time, I'll just say et cetera. Finish the rest of that. Okay. You could, if you forget this identity, you can put it on your cheat sheet. Cosine squared is 1 plus cosine 2 theta over 2. Okay, 15.911. Sketch the solid given by the given inequalities. Well, okay. Rho less than or equal to 1. Phi between 0 and pi over 6. Theta between 0 and pi. Yeah, I'm not sure if I did this one or something close to it, but I'm going to go all the way around to 2 pi. And then just imagine that we're cutting it in half, so to speak. Okay, so. Okay, so we're going out as far as a distance of 1. So the ice cream cone goes out to 1. Okay, phi is pi over 6. So if I start at the top, I come down to pi over 6, 30 degrees. And if theta was going from 0 to 2 pi, I spin all the way around, okay, which I can draw better. Have it. Okay, so this angle here is pi over 6 or 30 degrees. So here's what it would be if theta was going from 0 to 2 pi. You're only going from 0 to pi. I can't draw, but imagine instead of going all the way around, you're only going from here to here. And I don't even know how you draw that, but imagine taking half that cone and slicing it. Or better, imagine just cut it right here. You have an ice cream cone like that, and your cut is right down the middle like so. So you only have this part. Maybe I'll shade it in. Different color. Green. So the green is that half cone. I know it's kind of weird because we almost never see ice cream cones like that, right? You never take an ice cream cone, slice it like that. So it's perfectly half because the ice cream will probably fall off. And that, but that's basically what you have. From 15, 9, 11. Okay, so sorry if I did etc., but I brought you to the point where I think you can take it from there.
That Professor, that was 15.8, number 11.
That was 15.8. You wanted 15.9.
Yes.
Ah, okay, my bad. .9, 11. Oh, did I say to eliminate that one? If I didn't say it before, I'm saying it now. I think I said it, but if not, sorry. It was a little bit too difficult to do that one, so skip it. If you did it and you got it right, great, but otherwise it was too long. Oh yeah, I think
you did. Okay, never
skip
mind.
11.
Never mind.
Yeah, it's a nice problem, but too long. I said, some of these problems can get really, really long. Okay, let me check the chat. I think I'm caught up with the homework problems. I mean, the questions for now. Okay, I did that. All right, so I'm caught up. Anybody else, please? Otherwise, that's it. Wait a moment. Okay, I don't see or hear anything. All right, so Thursday, you have the entire class period for the test. You may start submitting the homework even now. And so right at started class time, which is what, 6:10? So just before that, I'll send by Canvas announcements the exam, and you have the entire class period for the exam, okay? All right, that's it for tonight, folks. So have a good night, and we'll see you on Thursday. All right, good night, everybody.
Thank you. Have a good one.
Okay, thank you.
Thank you.
Thank you.
Thank you. Good night.
Good night. Thank you.